All right, let's review from yesterday. We did a little bit of naming, so let's... Okay, let's look at these two here. What on the top one, what would be the parent name? Cyclopentane, because there are 5 carbons. What is this branch called? Ethyl. This one is methyl. So we need to decide which branch is carbon number 1. Is it going to be methyl or ethyl? Ethyl. And what rule are we following? Alphabetical. So we'll have 1 ethyl. And where's methyl? 3. 3 methyl cyclopentane. Okay, let's look at the bottom one. I was cut off here, but what is that? Cyclobutane, which is how many carbons? 4. Oh, yeah, sorry. So this is cis or trans? Trans. Okay, so then this one, we have dimethyl. How many carbons in methyl? 1. So I'm just going to, I'll do the cis part in a minute. So 1 methyl, and then 2 methyl. And 1 could have been anywhere. I could have started 1 right here, here, or there. That doesn't matter. How would I do cis? Give me one example. Both wedge. Or I could have done both dash. Either way, as long as they're the same, it's cis. We also look at the stabilities of the cycloalkanes. Which one's the most stable? Not, no, out of all of the, so we looked at 3, 4, 5, and 6 carbon. Cyclohexane was the most stable, and what was the least stable? Cyclopropane. Do you remember the angle for cyclopropane? 60. Do you remember for cyclobutane? Pentane? 108. And then hexane? Yeah. And what's the most stable conformation for cyclohexane? What do we call that? The chair. And then we also looked at axial versus equatorial. So if you have an axial branch, it's straight up or down, and then equatorial is, it's more stable, but it's also, yeah, left, it's like at an angle, right? Why is axial unstable? What's that interaction called? 1,3 diaxial. And that's just basically because it's so crowded, the electron densities are too close. Okay, and the last rule we didn't actually go over to yesterday. So we want equatorial, right? Our branch, if we could put equatorial, that's how we want it. The other rule is you want the largest branch equatorial. So sometimes you have a choice. You don't really have a choice. One of your branches is going to have to be axial. Okay, so which one do you make equatorial? If you have to choose one, it's always the largest. So the largest branch dominates. So let's kind of look at an example of that. Let me just make one up. Let's do trans 1 methyl 2 ethyl cyclohexane. So out of the two branches, methyl versus ethyl, which one do we have to make equatorial for sure? Ethyl. So the biggest one has to be equatorial. Now, if we can make both of them equatorial, that's the best scenario. Okay, but if we have to choose, then ethyl wins. Okay, what does trans tell us in a chair structure? Not the same, but opposite. Back there, yeah? It is, because I'm making it up in my head. Ethyl, I'll just switch those and then put a methyl, put an M there. So ethyl, methyl. Okay, so trans tells us what? They're opposite sides. So are we looking at direction or axial equatorial? Direction. So if one's pointing up, the other one is pointing down. And that does, axial equatorial doesn't matter, okay? Okay, so let's do this. So let's draw our first chair. Okay, so our first one, number 1, I use this one here, and I always just go up. Okay, why? Just it's a good starting point. So up at that point is what? Axial up. So ethyl, I'm going to put CH2, CH3. You could put it as a skeletal if you want. So it's up, axial. So then this one going to carbon 2, because it's trans, if this one's going up, this one has to go down. And down at that position, is that axial or equatorial? Axial. Because if I have axial up here, axial is down here. I'll make the key really quick. What was your question? Okay, so we'll this will work. So if we say, let me label the carbons. We'll say this is 1, 2, 3, 4, 5, 6. Okay. So we're looking at carbons 1 and 2. Okay. Trans tells us if this one's going up, that one goes down. Now that doesn't tell us axial equatorial. We have to determine that by the position. Okay. So if we go up here, so then carbon 2 we have to go down. So in carbon 2, which one's going down? Axial or equatorial? Axial. Okay, so let's see what we have here. We have a ethyl that is axial. and I'm going to put up axial. And then we have a methyl that is axial down. Right? Is this stable? No, this is about as, well, it is as bad as you can get. Both axial. So let's do the ring flip. So you reverse it. So this flap is going down now. This one's going up. Now when we flip it, what do we change? We only change one of these things. Do we change the way it's pointing? No. What do we change? Axial and equatorial. That's what changes. So the ethyl will now be what? Equatorial up. And the methyl will be equatorial down. So let's review this. Cis and trans just tells us if they're going to be pointing in the same direction or opposite directions. It has nothing to do with axial equatorial. When we ring flip it, we keep the way they're pointing, either up or down, the same. You don't change that. What you change only is axial and equatorial. So where is position 1 on here? Yeah, this bottom one right here. And that's this one if you want. That's position 1. That's position 2. So we need to change it to what? Equatorial up. So let's draw an equatorial up. And then on position 2, where is position 2? Go up 1 right here. And that needs to go equatorial down. So try not to draw it too ugly. Something like that. So between the two, which one is more stable? The one on the right, because we have both equatorial. It alleviates all of the 1,3 diaxial interactions. Going down? Yeah. That doesn't matter.
Why couldn't you start going down?
Technically you can. I just usually keep it the same, so then you don't have to think too much. But yeah, you can. And so if you said what? You said up equatorial. So then it changes your key. So then the next one would be down equatorial, and then that would be down axial. Yeah, anytime, let me see if I have my green here. Yeah, so let me flip this here. Okay, so do you see this methyl? This is a methyl right here. And it's having 1,3 diaxial interactions with these hydrogens here. They kind of move, I can kind of bend it over to even hit each other. I don't know if you can hear that. Okay, so the electron densities are too close. They repel each other because they are electrons. They don't want to be that close to each other. And that steric interaction, sterics is just fancy for saying crowded, okay? This crowded interaction can be alleviated if you do a ring flip. Let's see. And so my methyl is down here. Is it anywhere close to any of the hydrogens anymore? No. So when it's in equatorial position, it's a lot further away from the electron densities. It's not as crowded, so it's favorable. So basically, the axial position is crowded, and the equatorial is not. Okay, so in small groups, see if you can work on these two here. Let's do a cis 1, 2, no. cis 1-ethyl 2-methyl cyclohexane. And then let's do just a 1,4 dimethyl cyclohexane. So on the top one here, you're going to specifically look at the cis. On the bottom here, look at the cis and the trans. And tell me, so you're going to have a total of 4, right? Rings you're going to be doing when you include the ring flips. Out of all of those rings, which one is the most stable? And that will be the most stable conformation, either your cis or your trans. So let's say, I don't know, cis, you can have all of them equatorial, but trans you cannot. I'm just making things up. I haven't done it yet. So then the cis would be the most stable. So whichever one creates the most stable out of all 4 of them, that's your most stable conformation. Okay, so analyze those together, and then we will check them. All right, let's take a look at these. Let's look at the top one. So I went ahead and drew all my rings. So what does cis tell us? Same direction, okay? So it really doesn't matter how you start. Do you want to go up or down? Up. So let's go up, axial in position 1. So that's up, axial, and then skeletal. So then this position 2 for methyl is going to go up what? Equatorial. So I have ethyl is up, axial, and methyl is up, equatorial. And this up, that tells me it's cis. Okay? Now I'm going to ring flip it. Now I can probably just tell from right here which ring flip is going to be more stable before I even draw it. The other one. Why? Yeah, the ethyl is larger between the two, and so it will prefer to be equatorial. So when I draw this ethyl over here in position 1, it was an up axial, so now it'll be a up equatorial. And then my methyl was a up equatorial. Now it'll be a up axial in position 2. So this one wins because it has your larger group equatorial. Because you see, either way you have to have one of them axial. You can't get around that. So then you choose, okay, which one will have the most devastating effect if it's axial? And that would be the ethyl. It's the most stable structure. So in nature, they both exist, okay? But most of the time in nature is going to exist like that. Correct. The largest change is equatorial. Going back to the key, so if I start this one as an up axial, then right here, the next carbon is a down axial. So then, but I have to have this carbon going up because it's cis. If this one's going up, that one has to go up. Correct. So let's look at the next one. We'll work this out, but what answer did you get? Trans is the most stable? Okay, let's look at it and see. So y'all said trans. So I have 1,4-dimethyl cyclohexane. So I have, so we'll look at the cis first. So let's have them both going up. So if this is up, axial, right? Then 1, 2, 3, 4. What is this? Yeah, up equatorial. And so this up tells us cis. And so the trans will end up being up, down, always. So we have a up axial and an up equatorial. So position 1 was a up axial, so now it'll be a up equatorial. And position 4 was a up equatorial, so now it'll be up axial. So I have a axial, equatorial, equatorial, axial. And you see the branches are the same, so that doesn't matter. It's not like one's an ethyl or a propyl or something. Okay, so these are equivalent structures. So on the exam, if I ask which one's the most stable and I just give you this, they're the same. Okay, so let's look at the trans. So let's start again. This is going up, axial. So then over here, this would go which direction first? Down, and down in that position is axial. So we have a up, ax, down, ax. Okay, and then that would give us what? If this was an up ax, it changes to a up equatorial. And then over here, down axial turns into down equatorial. So we have a up, ek, down, ek. So we said this was the most stable. Why? Has all of them equatorial. So your trans is going to be the most stable. Yes, it also has the least stable one, right? That doesn't matter. The fact that it creates the most stable means it is the most stable conformation. So 1,4-dimethyl cyclohexane would prefer to be trans. And not everything would prefer to be trans. Sometimes they prefer to be cis. It's just depending on how many you can make equatorial. Okay, and those are questions like that are the ones I can ask on the exam. Okay, so if you're having trouble with those, kind of rework those out later. If you're still having trouble, then maybe listen to the vodcast a little bit in that area. And then if you're still having trouble, come see me or a friend or whoever you feel most comfortable talking to. All right, so let's look at the sapling here. Okay, so this one here goes over primary, secondary, tertiary, quaternary. This has to do with how many carbons you're attached to. Okay? So if we look at this first one right here, where my cursor is, how many bonds to carbon does it directly have? 1. So we call that a primary. What about this one right here? How many? Just look at the black lines. How many black lines coming out that area? 3. So what is this? Tertiary. This one up here? Primary. Here, here, and there. Primary. No. That's why I'm glad she brought it up, because I realized I haven't talked about it. And this says, yeah, it has 4 black lines coming out that spot, right? 1, 2, 3, 4. You didn't know why you got it right. So here, secondary. Does it make sense? So it's just how many carbons, not hydrogens, but how many carbons are bonded to that specific carbon. Primary means you're bonded to 1 carbon. Secondary means 2. Tertiary is 3. Quaternary is 4. Well, I mean, I haven't gone over, so don't worry that it was simple. It's a good one to do. Okay. So try, I mean, I know I did it here, but try it on your own later and see if you get the same answer. See if you're missing any. Okay, this one here. Yeah, so with methyl. So what's methyl? CH3. So we're going to do a 1,3 diaxial interaction with CH3, because that's what it says. So if we say that's carbon 1, where are the 1,3 diaxial interactions? How far away are they? 3 away. So we're going to count going clockwise and counterclockwise 3 away. Now this is axial, so this one actually makes it a little bit easier. They could have done it equatorial to confuse you. So this is axial, so we want the axial atoms. And they don't necessarily have to be hydrogen, it's just whatever's there. So let's count going clockwise. So that's 1 that you're starting on is with the methyl. 2, 3. Okay? So what is in a 1,3-diaxial fashion with methyl on this carbon? Bromine. Yeah, it's axial, so it's not necessarily hydrogen. It usually is hydrogen, but in this case, they put a lot of other atoms on there. So you go 3 away. So that's carbon 1. Then you count 1, 2, 3, going clockwise. Now we're going to do the same thing going counterclockwise. So again, this is back at carbon 1, 2, 3. Which one is? The hydrogen is the one that's axial. So there's your 1,3-diaxial interaction. Let's try. I think it'll do it with or without. Let me see. Correct. And I think it'll do it either way, to be honest. Let's go check again. Let's do the other way. So then nobody's wrong. So. That's true. If it pulls up. No. There it goes. Okay. So this time we're going to choose it. Correct. So either way is fine. But let's look at it this way. What if I, because I've seen them do this before. I don't know, this one will give you different things. But what if they said chlorine? That's what you have? Yeah, I think some people have different things. So let me reload this and pretend it says chlorine. Okay, now I know it doesn't say chlorine, but we're going to pretend it does. So chlorine. What position is it in right now? Axial or equatorial? Equatorial. So right now, would it have any 1,3-diaxial? No, so you're technically looking at the ring flip, okay? So when I ring flip this will go from equatorial to axial. So let's see if we can figure this out. Let's go. So if this is carbon 1, because that's what we're comparing. Now let's go 3 away clockwise. So 1, 2, 3. When I ring flip it, will the H or the Br be in a 1,3? Hydrogen in this case. Because you're looking at the ring flip. Does that make sense? Because when I flip this, hydrogen's equatorial here, but then will turn into axial. And then 1, 2, 3. So on this carbon, the OH. So it just depends. I've seen them ask it where they actually have the branch axial, and then I've seen where they have the branch equatorial. Okay? So it's just, if it's axial, it's easy. You're just looking for your axial positions. If it's equatorial, you're actually technically doing the ring flip, so you're looking at the equatorial positions. Even though at that, right now, do they have the ones I highlighted, do they have 1,3-diaxial right now? No, but if I ring flip it, they will. And so that's what it's actually looking at. Anyway. Does that make sense? Okay.
Well, that's not the answer, but it could be the answer if the question was different.
Correct. Well, some people do have, like you said, you had that question. Some of these questions are like, they ask different, like the same thing in a different way. Anyway, so I have no idea when they do that or not. And that's all of chapter 3. So chapter 3, let's see what you had. Chapter 3 is pretty big. Naming. Conformations, which would be when you rotate a molecule, so your staggered eclipse. Rings, and then the cyclohexane ring flip stuff. Chair. Okay, so let's start chapter 4. Let me introduce it, and then we'll take a break. Okay, so chapter 4, we're going to look at chemical reactions. Nope. Okay. You learned, hopefully, in general chemistry, your overall reaction. You're going to have reactants, which is your starting material, right? That's what's reacting together. And then what you produce, or what you make, is your product, okay? Reactants react together to produce product, okay? And typically we write it left hand as reactants, because that's how we read, right? Left to right. So the starting material comes first, then your product. Then there's a mechanism, and we're going to look at one type of mechanism today, which is not a very good representation of typical organic mechanisms, but nonetheless, we're going to look at it. Mechanism is a step-by-step pathway. So think of it this way. We want to climb up a mountain, okay? What is our starting point is where? The bottom. And where will our ending point be? The top, okay? The peak. Now, did I tell you how I got there? Are there several pathways I could have taken to get there? I could have maybe gone around. I could have rock climbed straight up. I could have taken a car, taken a helicopter. Right, there's several options to get to the top, is my point. Okay? A mechanism tells you exactly how you got to the top, if you want. It tells you how you got your product. So the overall reaction just tells you where you started, where you ended. But you have no idea how you actually got there. So the mechanism is all the steps in between. How did you make that product? Other things we'll look at are thermodynamics and kinetics. Just a little bit, don't worry. I say kinetics and people start crying. This is basically a study. This is like your K and your delta G. So it's really just a look at how stable your reactants are versus your products. Okay? If you end up with more reactants in the end, then they're more stable. If you end up with more products in the end, then they are more stable. So thermodynamics is just where the reaction is going to go. Is it going to stay more towards the reactants or the products? And then kinetics is really just how fast the reaction goes and how you can influence that. So like with temperature and stuff like that. So kinetics is speed. Thermodynamics is stability. Okay? Just because something's stable does not mean it's going to go fast. Okay? So you have to look at both of those. And this should be a carbon here. Yeah. So here is the mechanism we're going to look at. Okay? So this is the overall reaction. So let's kind of analyze this. Okay, this carbon, this is a methane. Do you see it has 4 hydrogens on it? Right here. Now let's look at the product. Now again, this is carbon, not hydrogen. Now it has how many hydrogens on it? 3, and what did it gain? Chlorine. So it lost 1 hydrogen and it gained a chlorine. Now over here I have Cl, Cl. And then over here it's HCl. So what did it gain? Hydrogen. And what did it lose? Chlorine. So do you see it basically those kind of switch positions? The hydrogen was there, the chlorine was there. Yeah, that's a C. That's not a hydrogen though. I'm assuming you're talking about right there. I did not make this slide. Of course I could have. It sounds like something I would do. But okay, so we're going to look at, that is the overall reaction. That's overall what happens. Now we're going to look at the steps of how that actually occurred. And this is called a free radical reaction. Do you know what a radical is? Yes, this is true. It is a lone pair or a lone electron in a pair. So there's a lone pair, which is how many electrons? 2. And when you have just a lone electron, you have 1. Electrons like to be paired up. Okay? So it's this very, very unstable single electron. So free radicals occur all the time. We see them in nature, in our body. This is what causes us to age and get cancer and everything else. So, can we stop free radical reactions? No. Just going outside, you're going to initiate a free radical reaction. Okay, but there's ways to not have as many, I guess. Okay, so there's steps. There's the initiation step of a radical. What do you think that means?
I think it gets it started.
What gets it started? Usually light. Propagation, this is sort of your middle steps. Okay? So you can initiate, you can start it. Propagation is kind of everything in between. And then termination, what do you think that is? The end. How do you stop the reaction? So we're going to come back and we're going to look at each of these steps individually and go through them. So let's take a break before we do that. start back up. Okay, so the first step in a radical mechanism is initiation. Oh, chlorine. Okay, so this is the overall reaction. Initiation. So this is where you're going to initiate. You're going to start the reaction here. In this step, you always split up the halogen to make radical. So we're going to create a radical here. And what's a radical? A lone electron. Okay, so out of these here, what's my halogen? Which one? What's my halogen here? In my overall? Chlorine. Okay, so there's my halogen. Do you see I have two of them, and they're bonded together right now? Is there a lone electron currently? No, so this is where we initiate it. And this bond between them is pretty weak, okay? And so you just need like light. You can put it literally outside under UV light, and it'll initiate this. Same thing as oxygen. Oxygen, you go out in the light, and it produces a radical. So I need to make a lone electron. So a bond has, if we look at it this way, has an electron on each side, right, from each chlorine. So what you're going to do is split this bond, put one electron on this chlorine, and notice, do you see that I use a single barbed arrow? And that means that I only moved one electron over. And then over here, I'm going to move that electron on that chlorine. And again, single barb. All of these arrows will be single barb because I moved one electron. So what do I end up with when I do that? If we follow the arrows, what do I get? Not a minus, not a plus. So let's look here. Do we see that? Do I see my lone electron? And, hold on, we'll do the formal charge in a minute. Okay, so they each have a lone electron, right? This electron went on that chlorine. This electron went on the other chlorine. How many do I have? 7. What group is chlorine in? So it's neutral. Radicals are neutral. Most radicals are neutral. Okay, but a radical is extremely reactive. This is about as reactive a species as you could get. Like a positive versus a negative, huh? Very, very reactive. Yes, so it wants to react. Light is what initiates this to happen. It's because you need energy to break that bond? Yeah, and you're going to get that energy from light. Light is just energy. Um, the, the sun's not really out, but there's still light, but it's coming from other sources. If anything, it would be almost nothing. Think about your UV, not your UV lights, but you know the lights that are initiated from sunlight, you know what I mean? So they charge themselves during the day, and then they come on at night. So it's kind of like that. So I would say if they do, it's very little. But you could just use a UV light. Yeah, you could. Yes. It still wouldn't be as much. So I don't know if it's enough to actually separate the moonlight, but from the sun. But possibly, I've never tried it. It could be an experiment. Maybe extra credit. Okay, so this is initiation. This is always initiation. Split up your radicals. Propagation 1. A propagation step is always between a radical and a non-radical. Okay, so your radical that you use is always the one we just formed. So what did we just form? Chlorine radical.
That would not be a chlorine ion, right?
Correct. Even though every once in a while I see books that put them in the category of an ion, but it's not technically because an ion is a charged particle. I would say no. It is. I grade your test. So now we're going to do a non-radical, so that means neutral. Okay, and the first one you'll use is the first one is your other reactant. So you see we have this reactant in our overall, chlorine. We already used that, right? We already reacted that. But do you see we haven't reacted this one? Yes. So that is our non-radical. This one? Oh, it will break up from this one. Okay, let's see what we're going to do here. So this is our methane. And overall, we said we're going to, what are we gaining? We're going to gain a chlorine, and we lose a hydrogen. You're going to lose first. Okay, so chlorine is very reactive. It wants to stabilize itself by making a bond. Okay, that's how it stabilizes itself. What are we losing in this? Hydrogen. So it's going to make a bond to hydrogen. It's going to steal it. So we're going to use this one electron right here, and it's going to react. And I know right now it's not reacting with anything except air, but I'll show you. And again, you see CH bond right here has the 2 electrons. So do you see the electron on hydrogen? It's going to come here and meet with that chlorine. So how many electrons make a bond? 2. So do you see 1 electron from chlorine is going to meet with 1 electron on hydrogen? No, this is a reaction. It won't have anything to do with dispersion. Radicals are destructive. They're going to tear things apart. They're going to break bonds. And the only bonds on here, do you see, are CH bonds? So it's going to just destroy one of your CH bonds. It's going to steal off a hydrogen. Why? Because it's well, in this case, it's the only thing to steal, but it's always going to steal the easiest thing. So we'll look at other ones where you have more choices of what it could steal. Okay, but I have this electron here, right? What do I do with that? You probably don't know. Yeah, it's pretty much just going to stay on carbon. Becomes a free radical. So let's see what we just did here. So I join, follow the arrows, a hydrogen with a chlorine. So what did I form? Yeah, HCl. Hydrochloric acid. Now, what about this carbon part? What did it just lose? Hydrogen. And what does it have on it now? Free radical. So do you see this is a product right here? Now let's look at our overall reaction. Let me pull it down. Do you see what's something I formed? HCl. So I formed one of my products just then. So your propagation, you will form your products. So this is, you want product number 1. Okay, so then we have propagation 2. And again, this is between a radical and a non-radical. Propagation is always between radical and non-radical. But now instead of losing, we're going to gain here. So remember I told you you're always going to use the radical that you just formed? What radical did we just form? The carbon. Okay, now this is going to confuse you for a second. So my non-radical always comes from one of my reactants. Okay, now let's look at what product have I not formed yet? This one right here, right? What do I need to form? So this is what I have. What do I need to get to that? Chlorine. So what do you think? What reactant am I going to use? Chlorine. Now let me further explain this. Because I always get, how is it still there? Because it reacted right here. And the answer is this. It's in the termination step, which we have not done yet. But radicals are very reactive. So if I have two reactive species next to each other, does it make sense they're going to react together? So this, even though these are forming like two radicals, they're also reacting together to come back to form chlorine, bonded together. It will, and that's a termination step. But if I have something extremely reactive and something extremely reactive, there's a very good chance they will react together. And they do. And these steps are all happening at the same time. We try to put a logical order to them, but they're happening all together. So as initiation is starting for one set of chlorine, propagation 2 is going on for another chlorine. Anyway, so the point is, these two, this will split up into this, then also very quickly split up into, or join to create this. Where some of it will come down to join to make this. So some of it's coming down here, and some of it's going back there. Okay? So this chlorine here is usually in solution. So now let's think about what we need to make. What's my reactive species? In here. Carbon radical. And what is it going to make a bond with? Chlorine. And we're always going to break up bonds. That's what radicals do. So this is going to react. And react with what? What did you just say? Chlorine, one of the chlorines. So that carbon electron is going to join with this chlorine electron. Now what do you think happens with this chlorine electron here? It's going to just stay there, really.
Can I ask a stupid question?
Yes, you can.
If the two chlorine radicals will join together,
Mm-hmm.
what's keeping the chlorine radical from joining with the carbon radical?
Nothing. It's a termination step. We'll get to that.
So basically, it could happen. We just don't look at it in this.
We will look at it. That is a possibility that will happen. We're just not there yet.
Okay, I guess the term that's confusing me then is a radical always joins the non-radical.
No.
Isn't that?
It can join, a radical and a radical can join, and we're going to call that termination. We just haven't done that step yet. But to actually call a reaction step, a mechanism step, propagation, that's when a radical reacts with a non-radical. Now, can it react with something else? Of course. But to call it a propagation step, it's always between a radical and non-radical. And if you want a radical and a radical to join together, that's called a termination step. So it's just by definition what you're looking at. But that can happen, and it will happen for sure. So here, what did we just make? We have carbon with these 3 hydrogens. And what is it bonded to? Chlorine. And what does that other chlorine look like? It's a radical. And I'm just going to draw that one lone electron. It has all the other ones around it. It doesn't matter. It's just as long as you have this bond coming off that carbon somewhere. Now comes your question. So then the other possibility that could happen is a termination. This is the only way you can stop a radical reaction. So let's look at this. When I join a radical and a non-radical, so in a propagation, do you see that in both of these, propagation 1 and 2, I form a radical in the product? So I have something reactive and I create something reactive. Okay? So termination, we're going to actually create something stable. Okay? So there's different choices here. And I usually just have you show me one. But this is between a radical and a radical. So tell me a radical we have formed in this reaction anywhere. Chlorine. And give me another one. Chlorine. We'll look at carbon in 1 second. Okay? I have a chlorine radical and a chlorine radical. All of the other lone pairs are around there. I'm just emphasizing this one lone pair, or this one lone electron. What do you think is going to occur? Yeah, it's a shorthand way. Just so I can really emphasize that lone electron. So what do you think they're going to do? Bond together. And what do I form? Cl. Yep, it's a Cl. And you can put the electrons around if you feel like it. So that's one possible termination step. What's another one? I heard somebody earlier say chlorine plus the carbon radical we formed. So what will they do? Bond together. That's a horrible error. Okay, so they're going to bond together. So I have CH3 bonded to chlorine. What's another possibility? There's one other one. Carbon to carbon. And again, those can join together. And form methane. So can a radical react with a radical? Of course. We just call that termination. Because look what we form here. I'm terminating the radicals. Because do I form a radical over here ever? No, I form a stable species. So anytime two radicals react together, I terminate those radicals. They're no longer reactive. So it's just how you're defining it. A radical and a radical will react, terminating itself. Or you could have a radical and a non-radical react, and that's when you create more unstable species. So it's sort of like this chain reaction. Yes? Here? This is where we're going to gain, if you want chlorine. Mm-hmm. Okay, now let's see if you can do it on your own. I have full faith in you. So let me give you the overall. The steps are exactly the same. Let's go crazy and put bromine in there instead. I know. It's a line. It's a bond. So here's the overall what's happening, so you can see. So over here, do you see that everything's happening at this carbon? See, CH3, CH3. The CH3, nothing happens there, right? They don't change. It's this carbon here that changes. So here it has how many hydrogens? And then over here it has 1. So it lost a hydrogen, and what did it gain? A bromine. So see if you can write out, and just flip back and forth. It's the same steps. Yes, these are slightly different, but that doesn't matter. You can see what's going on. See if you can figure out the initiation, propagation 1, propagation 2, and termination steps for this. And we'll check it. All right, let's take a look at this. And then I'll let you go. What's going to happen with initiation? Yeah, we're going to break up the bromines. And what do we form? 2 bromine radicals. When you're doing this on sapling, make sure you use the single barbed arrows. So 2 bromine. You could write bromine, bromine, or just there's 2 of them. Everybody okay with that one? Propagation. So propagation is between what? Propane. So a radical and a non-radical. So we're going to use bromine radical plus our propane. And then let me actually do this. Make one of them into a bond. Okay, what is bromine going to react with? Hydrogen, and that's why I wrote that as a bond. So those will react together, and then where will that electron stay? On carbon. So what did I form right here? HBr. And where is the radical located on here? Yeah, that's central carbon there. What radical do I use right here? The propane radical. Oops, CH. And what is it going to react with? The 2 bromines bonded together. Okay, so this carbon's going to make a bond with what? One of the bromines. And then this electron will stay on itself. So I'm going to have a bromine radical. And then if I write it down here, CH3, CH, CH3. And where's the bromine? That second carbon. So what? Yeah, there's a plus. This was, and then what did you ask? Yeah.
What would you call it before bromine interactions? The carbon radical?
You would just call it a propane radical. Okay, then termination is always between what? 2 radicals joining together. So let's look at all our possibilities. Give me one. Bromine plus bromine. Yeah, so bromine, bromine, and what do we make? They're 2 bonded together. Then you said bromine, propane. Those 2 radicals there. No. Here. Bromine, bromine, or bromine, propyl. And then I ran out of room. And what was the last choice? Yeah, the 2 propane radicals.
Now, wouldn't the termination reaction be more desirable for the chemicals themselves, or they really not care?
What do you mean?
I mean, since there's no bond that has to be broken for that to occur, wouldn't they rather do that than break the bond?
The thing with radicals, they're very destructive and extremely reactive, so they're not selective. Now, what's easier for them to do would be the termination. But they'll literally react with anything they're closest in contact with. So if they happen to be closer to a non-radical, that's what it's going to react with. If it's closer in contact with another radical, it'll react with that. So it doesn't care because it's so destructive. But energy-wise, this is going to be a lower energy. So when these, oops, did not put that on carbon, react there.
She likes the truth.
Don't put truth there. Pretty much what I try to do, just don't do. Yeah, I understand that. We didn't mean to do that.
You made that mistake.
So look like this, right? Essentially, because it's the two CHs, not twos, that will join together, right? Okay. No. And maybe you can follow my arrows. So.
Are these, is it like the opposite of the two barbed arrows where they're always going with each other? These are always going against each other?
Correct.
Like the residencies are always chasing each other.
They're always chasing each other, yeah. And anytime you do double barbed arrows, they're always going to be chasing each other. Most reactions in organic chemistry, most mechanisms even, use double barbed arrows, meaning removing 2 electrons at a time. This is the only type that uses single barb, and this is the only type we'll ever see, and it's the only chapter we'll ever see it in. So look over those. I don't expect you to have it all memorized by now, but if you can at least follow your notes with it, then you're in good shape.
Test tomorrow, right?
Tomorrow, yeah. You can show up, see if I'm here.